Now coming to the history of nanoscience and nanotechnology. Colloidal gold, gold, very fine gold, when people did not know that it is nanoparticles of gold, there was a term called colloidal gold. And in physical chemistry, we study colloids, like milk is a colloid, blood is a colloid. You know, there are many things which uh, form colloidal solutions. So gold can form colloidal solutions. This was known in 2500, 400 years back. And it has been used in making in the glasses colloidal metals like gold, silver, copper. Many of them have been used to give colors. This is a famous glass, a cup, which has made of metal and glass. The glass sometimes gives you red color, sometimes gives you green color, depending on light is inside, coming from inside or outside. Okay, basically that means we are looking at transmitted light or reflected light. This color of red and green is basically because there are gold nanoparticles within this glass. And this was made by people who did not know that nanoparticles are being formed. The way they were making the glass, you know, glass is you heat silicates to very high temperature in some material. So if you can use a copper vessel in those days, copper vessel or silver vessel or gold vessels were used. So when you melt silicates, some of this copper, silver, gold will go into the liquid, the molten liquid. And when it solidifies, it will form a glass and it will give a color because now these small particles of gold, silver have gone into the glass. And that gives rise to the colored glasses, which you see all over Europe in churches, even in Goa, etc. You can see church which have got glass, which are colored glasses. And these colored glasses, now we know, actually are colored because of some small particles of gold, silver, copper, depending on what kind of vessel was used to make the molten liquid from which glass was made. Apart from that, in Ayurveda system, they used to use very fine gold and silver as medicine, and has been used. Now, of course, there are a lot of scientific studies on what these gold, silver particles, which are nanoparticles, do in the body. So there is this old knowledge of particles, which today we know is basically due to metal nanoparticles. The first time in the laboratory, gold nanoparticles were made was by Michael Faraday in 1857. And you see these red solutions are of the colloidal suspension of gold. Even Faraday called it colloidal suspension of gold because he did not know that it had what are nanoparticles. So he called them colloidal suspension. Later on, these particles, if you take a drop and put it on a grid and take it under the electron microscope, you will see this kind of structures where each dot is a gold atom. So you can see atoms of gold from this solution. So there are gold nanoparticles, which are, this is a nanoparticle, and inside the nanoparticle, you can see atoms of gold. Okay, high resolution transmission electron microscope will give you this kind of feature. So gold was made in the lab in 1857, and it's stable solution. It is pink in color, but the colors depend on the size of gold nanoparticles. Okay. More recently, in 1985, carbon-based nanoparticles were made, and they were called Buckyball because of the structure given, found was like the structure given by an architect called Buckminster Fullerene. He made a dome which was half of this. If you cut half this molecule, the upper half is actually forms like a dome. And this dome is built in Canada in some place in 1970s. And so when they formed this molecule, C60 molecule, this was called Buckminster fullerene based molecule. And in short, people call it Buckyball, but actually it is C60 molecule. There are 60 carbon atoms arranged in pentagons and hexagons. So you can see there are 5-membered rings and there are 6-membered rings. So depending on a number of 5-membered and 6-membered rings, you can make many, many buckyballs. This is C60, okay? It has 60 carbon atoms, but you can make C72, C78, C84, many of them you can make. C540 is also known, depending on the structures, and people have studied why certain numbers are more stable, why certain number of carbon atoms. So this is why this is a nanoparticle, because the diameter of this particle is less than 1 nanometer. It's 0.7 nanometers. And these are buckyballs, as you see, and you can put molecules inside them. These are called endohedral molecules. But we can also make carbon nanotubes. These are spheres, but we can make nanotubes with hexagons. And if you want to close them, you can close them with pentagons. So these are very famous. Carbon nanotubes are among the most important materials discovered by mankind. It has so many applications. Even carbon nanoparticles have lots of applications, but carbon nanotubes have many applications. You can have single-walled carbon nanotube if you have only one layer, but if you have multiple layers, then it is called multi-walled carbon nanotubes. And these were first seen by Ijima under an electron microscope in 1991. So why people are interested in nanoparticles and nanotechnology? Because nanomaterials, which are of the order of 1 nanometer, say they have 3 to 5 uh, atoms, or maybe more than 5 atoms, they are of a thickness much smaller than the thickness of one strand of your hair. Okay, they have a lot of interesting properties, electronic properties, physical properties, chemical, all of them change. So you have the same gold, but different size, its property will be different than your normal gold. If you have silica particle, normal silica, SiO2, will be very different from nanometer size silica. So electronic properties will change. You will see quantum size effects, single electron tunnelings, the melting point will change, the hardness will change, the catalytic properties will change, reactivity will change. So all properties change with nano size. Material is same, the molecular formula, the compound is the same, but the size is different, the property is different. And why are they different? To a large extent, because of two reasons. One is electrons get confined, so you start seeing quantum effects. The other is surfaces become important because the surface area increases as the size of the particles decrease. You have huge surface area, so surface properties change. Examples: gold small particle does oxidation of carbon monoxide to carbon dioxide. Micron size particle does not do. The normal gold does not do. You can have different color butterflies because of the size of structures on its wings change from in nanometer, from few nanometers to more nanometers, and it scatters light of different wavelength. So it becomes blue in color or brown in color, depending on what are the pore size in the wings of the butterfly. And this is natural, but we can make it in the lab. And the lab, what we study, that today in physics we call nanophotonics. That means same material, I can have different colors by making different size holes within the surface of a material. It can be a plastic, it can be stainless steel, it can be aluminum foil. I can make nanometer size holes, I can drill on the surface, and I can pass a beam of light and I can get different colors. depending on the size of the holes and the periodicity of the hole, the array of the holes. How do I array one hole and the next hole? What is the difference in the distance? If it is 5 nanometers, I will get some color. If it is 10 nanometers or 1 nanometer, I will get a different color. So I can tune the color. This is very important for strategic defense purposes, and also in textiles and all these things, we can change colors with the same material. Magnetism can be changed. Iron is magnetic. All of you study that in school, but I can make non-magnetic iron by just changing the size of iron particles. Gold, I already told, can change colors from yellow to blue to red, orange. I can make green colors, gold, all kind of colors of gold I can make in solution. Unfortunately, you cannot wear the green gold like a bangle or this thing, but you can make gold coatings. You can make gold coatings of that color, but solid gold is bulk gold is micron size particles, gives you yellow color, which is the natural gold which all of everybody wears. The melting points change. So this is gold. Normal gold has a melting point of around 1250 Kelvin. That is around 1000 degrees centigrade, 980 degrees centigrade. As I change the size of the particles of gold, the melting point decreases. And if the particle size is 50 angstrom, this is angstrom. Okay, that means 5 nanometer gold. Then the melting point will be around 1100 Kelvin. That means it is around 850 degrees centigrade. I make it smaller, say 25 angstrom, that means 2.5 nanometers. Melting point will be around 500 Kelvin. That means 275 degrees centigrade. That means from 980 centigrade, I can bring it down to 250 centigrade, the melting point of gold, by just changing the particle size. So surface area is important, because if I have 1 cube of 1 meter, I have less surface. If I cut it into small pieces, the same material will have so many exposed surfaces, and so surface area will increase. All the things which happen on surfaces will increase. That means reactivity will increase. Okay. Another thing will increase when surface area increase. The dipole moments which are on the surface are disordered. So whether they are electric dipoles or magnetic dipoles, depending on the material, if I decrease the size of the particle, the surface will increase. So I will have less ordered dipoles. You see, these are ordered inside the particle. On the surface, it is disordered. But if my particles become smaller and smaller, then most of it will become disordered. And so in physics or material science, you study ferromagnetism or ferroelectricity. Both ferromagnetism will become paramagnetism as the particle size decreases, and ferroelectricity will go to change over to paraelectricity when the particle size decreases. Melting point decreases with size because the number of shells of atoms changes. As you see, if you have a very small atomic cluster, there are 13 atoms, one atom at the center and 12 surrounding it. It's a 13 atom cluster, and you can see that you will have a surface atoms is 92% coverage for the small cluster. That means 92% of the atoms are on the surface of the cluster. Whereas if you go to 1415 atoms cluster, the cluster is made up of around 1415 atoms, then the percentage of surface atoms is only 35%. That means most of the atoms are now inside. They cannot see the outside. That is why the activity decreases when you go to a cluster of the same material with large number of atoms. So small number of atom cluster will have high reactivity because 92% of the atoms in a 13 atom cluster is on the surface. So it can react with anything which comes close in contact. So surface chemistry becomes important, surface physics becomes important and all that. Okay. The colors change. All of you might have heard of quantum dots, right? What are quantum dots? These are semiconductor nanoparticles. So quantum dots of semiconductors, example, cadmium selenide, cadmium sulfide, cadmium telluride. I can take one semiconductor and give you solutions of different colors. How? By changing the particle size of that semiconductor. If you take cadmium selenide and change its particle size, it will show you colors from red to blue. Why is it happening that the same material in a solution of cadmium selenide shows me different colors? This is because as I change the size, what happens to its conduction band and valence band and the band gap? So this in semiconductors, we study about band gap. That is the difference in energy between the higher energy unoccupied states and the lower energy occupied states. In molecules, we study in chemistry orbitals. But in a solid, orbitals, there are many orbitals, millions of orbitals. So they combine and become a band. And so in a solid, we call a valence band made from the lowest occupied molecular, highest occupied molecular orbitals. So these are actually also called HOMO in chemistry. Those orbitals combine to become the valence band in a semiconducting solid. And the lowest occupied molecular orbitals, that means those which are unoccupied molecules, when those molecules form a solid, now we don't have orbitals, we have band formed from those LUMO orbitals, and that is called the conduction band. Now the difference in energy of the highest of the valence band and lowest of the conduction band is called the band gap. Okay, because this valence band will have a width of energy. This is called the bandwidth. So you go to the highest of the valence band and lowest of the conduction band, and this gap is called the band gap. And I can change the band gap and I can change the color. Because the color comes from the light which the solid is absorbing. The solid is absorbing light equivalent to the band gap. If I increase the band gap, high energy light will be absorbed because the band gap is high. And you will see a complementary color. Okay, so when the band gap is high, it is absorbing in the blue region. Okay, lower wavelength, high energy, right? So automatically you will start seeing different colors depending on what is the band gap of the nanoparticles that you have made. And the band gaps will change with the size of the nanoparticle. If you have small size, it will absorb very small energy. So you have a complementary which is very high, and you will not see that. If you have in the middle, these are absorbing in the visible range. So you will see a complementary visible color, whatever it is. So you will see red, green, yellow, orange, depending on variation in these sizes. So band gap is low, you will see a red color. Band gap is high, you will see a blue. Okay, blue color will be absorbed. Blue energy will be absorbed. So this is the historical development I said, from glasses 2000 years back, in Ayurveda, Unani, then Michael Faraday in 1857. But the more modern development of nanotechnology is after Feynman. Richard Feynman was a physicist. He gave a lecture at the American Physical Society meeting held in 1959, where he talked about a principle called doing science at very small size, very small length scales. He did not talk about nanotechnology or nanoscience, but he created this idea. What happens if you look at within a molecule or within 10 molecules? What kind of properties you can control or you can make? What if you arrange 10 atoms in one pattern? How will that pattern interact? Can you make a molecular wire with 100 atoms? Can you make these kind of basic fundamental questions was raised by Feynman, and he said nothing is known about this, so all scientists can work in this area. So he said there is plenty of room at the bottom. Here bottom means at the small size, and plenty of room means lot of work can be done. That is what it means by plenty of room at the bottom concept, first raised by Richard Feynman, who won the Nobel Prize for electrodynamics. He was a very, very intelligent man. People sometimes refer to him like Einstein, or sometimes people even say better than Albert Einstein. And Richard Feynman was a professor at Caltech. The other thing happened after that was a mechanical engineering subject is called micro machining, where they try to do machining on metal sheets like aluminum sheets, stainless steel sheets, and they try to do finishing such that the surface does not have any rough nature. That means the surface does not have structures which are has valleys and crests, that is micron size structures. They want to make it very smooth. So when he was doing that, he said, if I do at nano finish, I will call it nanotechnology. He was the first one to coin the term nanotechnology. After that, at MIT, a student talked about concepts about robots working inside the body, etc. His name was Eric Drexler. He first talked about machines inside our body. Although he never did any technology, he wrote books and he wrote papers which were like science fiction at that time. And his books have been converted into films. And several books are there. One of them is Engines of Creation. How can machines work inside the body? What are nanobots, nanorobots working inside the body? And after that, the major breakthrough happened was the invention of AFM and STM. In 1986, uh, uh, atomic force microscopy, first scanning tunneling microscopy was invented by two people in Zurich, ETH Zurich in Switzerland, and they got the Nobel Prize along with Ernst Ruska, who invented the transmission electron microscope long back. So TEM was known long back from 1939-40 onwards, but the Nobel Prize was given together with AFM, STM, and TEM to three people for microscopy. The STM and AFM directly brought about a revolution in nanotechnology after the 1985-86. And real nanotechnology started in the world around that time, around 85-86. And probably in India, nanoscience and technology started sometime around 95, 98, 99, etc. So this is Richard Feynman, who said there is plenty of room in the bottom. 1959, very, very smart, intelligent, and highly decorated scientist. This is Eric Drexler, who wrote about molecular manufacture, how to make molecules like machines, which will work in our body or in a machine like small machines. He wrote this book of Engines of Creation. And these are the kind of molecules you see with atoms. Can we build this kind of a rotor? And actually in nature, in our body, we already have such machines. We have ribosomes, which are actually work like machines in our body, which make molecules. So the ribosomes are called molecular assemblers. So he said, can we make in the lab such machines which are molecular assemblers? So this is the atomic force microscope, which was invented very soon after the scanning tunneling microscope. This was 1986, and I'll come to the scanning tunneling microscope. The atomic force microscope looks like this. It has a cantilever which moves on the surface, and the cantilever has a very fine tip. This tip is very, very fine. and it goes very close to any sample you want to study, and it measures the force between atoms. So the cantilever tip has some atom and the sample has some atom. It measures the force, very, very weak force, which we study in school, college as van der Waals forces. But this is very sophisticated. It can measure very weak forces. And depending on the force at one point and the force at the other point, it creates a map. And depending on that, it tells you which atoms are where on the surface and many other things it can do. Basically, this cantilever is pushed up or down depending on the force. So you can imagine how small the force is, how small will be the movement of the cantilever, and how powerful should be the detector to detect that small change in the position of the cantilever. So the cantilever will move a small amount because the force here is in piconewtons, 10 to the power minus 12 newtons. So the cantilever tip will move very, very little. You cannot imagine how small this force is. But still, the detector is so powerful that it detects even that small movement of the cantilever. And then we have some equations to convert the position where this reflected laser beam falls from to the force on the surface. We can calculate that, and based on that we can make a map all through some. You need a software and a computer to do all these calculations, so you have to develop appropriate algorithms, but these are now sold by companies along with the machines, and you can make a map of the surface using atomic force microscope. This is what is happening. This is the physics of the operation. That is, the tip is pulled down, so there is a binding force. It comes when the tip comes very close, then there is a repulsive force. So we have a repulsive regime and an attractive regime. These are all we can study in this motion of the cantilever, which allows us to measure the force. That is why it is called atomic force microscope. And using that, we can study surface topography. We can study where are the atoms, if there is any atom missing, if there is a nickel atom or a cobalt atom, minor changes in the atoms and the structures. We can see whether they are spheres, they are rods, many, many things you can study on the surface. This is the simplest thing. You can study more complicated things. You can study reactions on the surface. You can study cell growth and many, many things. This was the first scanning tunneling microscope. Looks very complicated because it was made in the lab by hand. But today's scanning tunneling microscopes look much more simpler, made by commercial houses. This was made by scientists in the lab. You need a chamber. The chamber has to have vacuum, ultra high vacuum. Scanning tunneling microscope is little bit more complex than atomic force microscope. That is why you will see in the world today, atomic force microscope is more popular because biologists, chemists, physicists, everybody can use. Whereas STM, more or less, is used by electronic people, physicists, electrical engineers to some extent. It is more sophisticated, needs more handling, more careful handling, and is also a little bit more expensive because it needs UHV situations, etc. So this is what it does. This is the STM tip. In this case, the tip is really an atom. In an AFM, the tip may not be an atom. It can be few atoms. But here it is a real one atom. Normally, these tips are made of tungsten or many other things. And it goes near a surface. When it goes near a surface, it interacts with one atom of the surface and there is a tunneling current. So the tip atom and the surface atom, in between, there should be tunneling. Tunneling will happen when you are in quantum regime, very, very small distances. And then you can measure the tunneling current. Measuring the tunneling current tells you about the atom present on the surface. It tells you where certain atoms are there, where certain atoms are missing. So you can measure the entire surface. I can move the tip and you can see how the tip is moving in a zigzag manner. And this motion of the tip on the surface is called a raster scan. RASTER. It is called a raster scan. That means you are scanning the surface using a tip and you are measuring, the computer is recording the tunneling current from each point. And after that, using an algorithm, that tunneling current is converted into an image, which will tell you which atoms are where. So these are gold 100 plane studied using an STM. And this is basically the electronics of the tip sample and how the feedback mechanism is working for the STM. This is, of course, the transmission electron microscope. This is very, very powerful. This is among the latest transmission electron microscopes. These are different from atomic force and STM. The TEM was invented in 1939, 38, etc., or even earlier. But it was commercialized also in the 1940s. And every few years, there were improvements. And now the world's latest electron microscope is called the aberration corrected high resolution transmission electron microscope. Today's latest one can cost you around 30 crores to 35 crores. Actually, it has power to see even within the atom. But it is very difficult to maintain this machine. You need to have a lab which has no noise, no electromagnetic noise, no even air current should not be there, because it is very, very sensitive machine. So you have to preferably work with remote. That means the operator should sit in another room and the machine should be in another room, so that even when you are breathing in the room can affect the stability of this machine. This is so sensitive. And if you work with that kind of sensitiveness, you can get the power of this machine, where you can certainly see atoms, you can even see within the atoms. This is called the aberration corrected high resolution transmission electron microscope. This is also, you have to salute scientists. You know, in physics, we know that there is something called a diffraction limit. That means you cannot see something below the diffraction limit. But there were scientists who found methods to go about. You cannot change the law of nature, but you can circumvent the problem by other means. And they circumvented that by using what is called aberration corrected methods. And when, and you can now see images much more clearly by going around this aberration correction, which was earlier not possible. This CS correction was earlier not possible. There are different types of aberrations, but one of these aberrations is the CS corrected. You need to use special electromagnetic lenses to take care of that. And that was a breakthrough in 2005 by scientists, and they were given the Nobel Prize